Hello everyone. In this video we're going to talk about how to find the derivative of something that is basically impossible, such as 0 over 0 or infinity over infinity, and those are types called indeterminate forms. Now in a previous section, in chapter 3 or 2, we did do this, but we did it by simplifying the function itself, and sometimes that's not always possible. So instead, what we have is this thing called L'Hopital's rule. And L'Hopital says that if we have two functions that are continuous and differentiable over the interval, whereas the denominator cannot be 0, if we take the derivative of both the numerator and denominator and then apply the limit, then we can use that to evaluate. So this is easiest to understand when we're looking at an example. So let's see here. We want to evaluate the limit as x approaches 1 of this lovely function. Now if we went ahead and put in 1 with using direct substitution, we're going to get 0 over 0, which of course we can't work with. So L'Hopital comes along and says, well, let's get the derivative of the top and the bottom and then apply the limit. So we'll want the limit as x approaches 1 of the derivative of our top, which would be 3x squared plus 2x minus 2, over the derivative of our bottom, which is just 1, and then apply the limit. Okay, well, now if we use direct substitution and we put 1 in for x everywhere, we're going to get, well, that looks like 3 plus 2 minus 2, so that'd be 3 over 1, otherwise known as 3. So with L'Hopital, we can actually evaluate, whereas before we had to kind of hand wave it. All right, so let's do it again. So we want to find the limit as x approaches -3 of these two functions. Now if we put in -3 for our x and evaluate it, we would get 0 over 0, which doesn't work. So what we're going to do is we will find the limit of their derivatives. So the derivative of our top would be 2x plus 8 over the derivative of our bottom, which is -5 plus 2x. Now apply the limit. Direct substitution, -3 in for both x's. You can use your calculator if you'd like. 2 times -3 is -6, plus 8 is +2 over -11. And there we are. That's all we need. So what about e's? Well, if we're working with e, well, you guys know how the graph looks of e to the x. If you're approaching 0 of e to the x, you're not going to work so well, is it? And same thing. So we take the derivative. So the derivative of e to the x is e to the x minus 1 over 2x. Put in 0 and, uh-oh, you get 0 over 0 again. Oops. So we can't do that. However, we can apply L'Hopital for a second time. All right. So the derivative would be e to the x over 2. Apply that. Now apply the limit. We would get 1/2, and it works fine. So you can apply the limit more than, you can apply L'Hopital's rule more than once. It's not fancy, but it does work. All right, what about square roots? Well, same principle. So if you went ahead and put 0 in using direct substitution, you would get 0 over 0. We can't do that. So we take the derivative. So the derivative of square root, well, that doesn't really work so well, does it? We're going to have to finagle this. The derivative of the bottom is just 1, but the derivative of the top doesn't work, does it? So we are going to have to do this the old-fashioned way. Scrap paper. So if f is, now let's change that to 9 plus 3x to the 1/2 power. Remember that the square root is the same thing as a 1/2 power. There we go. Which that would give us the chain rule. 1/2 minus 1 would be negative 1/2. And then times the derivative of the inside, which would just be 3. So that would give us 3/2, 9 plus 3x to the negative 1/2 power, which is not pretty, but let's see here. Let's see if we can make it pretty. A negative exponent will tell us that the is in the denominator, so that would be square root 9 plus 3x. That way. Okay, there we go. And since the derivative of my bottom here is just 1, that means that I'm just taking the limit as x approaches 0 of that lovely blue. Anything over 1 is just itself. So that's easy enough. And then we can apply the 0. In this case, we don't have to apply it twice, the L'Hopital. We can just do it the once. We just had to have that lovely side note of chain rule and the power rule. So we apply 0, and that will give us, let's see here, that'd be 3 over 2 square root of 9. So that'd just be 1/2. So L'Hopital's rule is very, very handy. We can evaluate indeterminate forms of 0 over 0. All we got to do is take the derivative of the top and the bottom, and it works fine. The fun part is that it works for other indeterminate forms as well, including infinity over infinity. And once again, all we really need to do is take the derivative of the top and the bottom. As long as our denominator does not equal 0 on the front end, we should be fine. So let's put this into practice. Evaluate the limit as x approaches infinity of this lovely thing. Well, if we went ahead and graphed each, it's a cube. So this does wee, which means it does wee, and we can't do that. So we apply L'Hopital's rule and find the derivative of each. So that would give us 12x squared minus 12x over 6x squared minus 10. Can we apply the limit now? Well, that's a square, isn't it? A square graph does that. So if we applied the limit now, we would still get infinity over infinity, wouldn't we? So we can't do that. So let's apply L'Hopital again. Derivative of the top would be 24x minus 12 over 12x over 12x. There we go. Can we apply the limit now? Well, x is a linear graph, isn't it? And that is positive, so it does that. Which means if we apply the limit now, we're still infinity over infinity. It still doesn't work. So we apply L'Hopital one more time. Let's see if we can get it this time. The derivative would be 24 over 12. Okay, now that we can do. And that would just be 2, of course. So you can apply L'Hopital as many times as you need to get the to evaluate the limit as you are required. So how about something like this? And I don't know why that should be ln x over cosecant x. And do notice that we are specifically evaluating the limit as x approaches 0 from the right. That little plus sign means from the right. So in this case, ln of x, if we apply the limit, that would give us, well, our numerator would approach negative infinity, wouldn't it? And then for cosecant, as we approach 0, that would be positive infinity, which is still infinity over infinity. We can't do that. So we have to apply L'Hopital instead. And if you can't do it in your head like I just did, visualizing the graph and then evaluating, write it down. There's no problems with that. The only difference is I've had lots of practice in doing this. So draw it out. What does the ln graph look like? What does the cosecant graph look like? And then you can see the limit graphically. Whatever works. So the limit, not the limit, the derivative of ln x is 1 over x. The derivative of cosecant is negative cosecant cotangent. Can we apply the limit now? It's a little bit harder because, I don't know about you, but that's just looks weird to me. Let's simplify this yucky stuff. Let's see here. I mean, we got too many fractions. So cosecant is, 1 over sine, and cotangent is cosine over sine. And 1 over x, so that would be shifted and flipped, right? So that would be sine over 1 times sine over cosine 1 over x and a negative. So that would give us negative sine squared over x cosine x. Right. Limit as x approaches 0 from the right. There we go. That's a little bit easier to see. One fraction is enough for me. Okay, so now let's see if we can apply the limit. Once again, this is a little bit harder to visualize, but that's why we have calculators, right? So, negative sine squared x, well, sine squared x would just be sine times sine, right? So sine graphs do that, and so do cosine graphs. And that will give so sine x as x goes to 0 is 0. And cosine as x goes to 0 is 1. However, we have this x right there. Well, that's definitely going to go to 0. So we get 0 over 0. So we started with negative infinity over infinity, and now we have 0 over 0. Well, that still doesn't work, so we have to apply L'Hopital again. Fortunately for us, even if we're going from infinity to zeros, the process is the same. Find the derivative of the top and the bottom. So the derivative of sine squared, if we finagle that, that would be... I needed to move things around a bit to make it work. You may want to pause the video to make sure you understand where everything went. I rewrote sine squared as sine times sine so we could apply the product rule to find its derivative. The derivative of sine is cosine, so that added together to give us 2 sine cosine. I had to do the product rule again for my denominator. Derivative of cosine is negative sine, so that's where the negative came from. So pause the video and make sure you understand where everything went. Now this one is a little bit definitely harder to visualize, so actually drawing it out is a good thing. 2 sine cosine is just going to be a variation of the sine graph with a bit more wiggle to it. So the limit as x approaches 0 would be 0. So the cosine minus x sine x, that would be very similar to the cosine graph, but this time we'll have a lot more wiggle. And, oop, that's not right. Do something like this. There we go. So that would be 0 over 1 as x approaches 0 from the right. Use your calculator to your advantage, or online programs such as Mathway or Math is Fun. Both very helpful for these kinds of things, because it's really hard to visualize when you start messing around with the base graphs that we're so familiar with. We haven't memorized these types of things. So use them to your advantage. Now, since we don't have 0 over 0 and we don't have infinity over infinity, we can actually apply the limit this time. So the limit as x approaches 0 from the right would be negative. Remember, we do have that lovely negative. 0 over 1. This is an actual number, and that number is 0. Just because our answer is 0 does not mean we're wrong. So we can do this as long as we have L'Hopital to fall back on. We have infinity over infinity, or we have 0 over 0. Whether it's positive or negative, we don't really care, as long as it's in one of those two forms. Now, that's not to say that we can't find the derivative of other types of indeterminate forms. It's just a little bit more interesting. So in the next case, we're looking at forms of 0 times infinity, or infinity minus infinity. So if we have something like 0 times infinity, which this lovely example is, x squared, as x approaches infinity, that's definitely 0. And sine, well, sine or cosine, if you're going to infinity, that's going to be infinity. So we do have this form. Now, because of that, we need to fix it. L'Hopital is wonderful, but it doesn't really work for other types of indeterminate forms, unless, of course, we make it work. So what we're going to do is we are going to finagle this algebraically so that we can apply L'Hopital. So we can't do L'Hopital yet, but we will be able to in a minute. So we got to finagle it first. So how do we do this? Well, algebra. We know what we need. We need either 0 over 0 or we need infinity over infinity. So let's see how we can do this. Let's divide by the reciprocal. Alright, let's divide by the reciprocal. So to be able to do that, we're going to, let's split this, because that doesn't work. So sine of 1 over 4x squared over, well, if I can't do 1 over x squared because that's technically a denominator, and x squared that they gave me is a numerator. However, if I do that, it would work. So 1 over x squared. Yeah, let's do that. So does this... Yeah, that'll work. So we divide by the reciprocal. We rewrite it. And does that work? Can we now apply L'Hopital? Well, let's see. 1 over x squared as x goes to infinity is going to give me 0. And sine... well, didn't we just say that that was going to give me infinity? So, as x goes to infinity, so we are going to, yeah. Okay. So that'll give me the chain rule for my derivatives. Oh boy. Okay, let's see here. So chain rule of my top, that is derivative of sine is cosine times the derivative of the inside, which would be 1/4 x to the, nope, that's not right. 1/4 negative. There we go, that's better. Because this is the same thing as saying 4x squared to the -1, right? So that'd be 4 to the -1 and x to the -2. And we can do that way. That's what I did. Okay? Alright, that'll work. And that is multiplying by negative, not subtraction. Okay. Derivative of the bottom is so much easier. That's -2x to the -3. Yay! Okay. Limit as x approaches infinity, because that was actually the goal. Okay, let's simplify this. Don't you just love it when they make it interesting? Okay, so those two things will cancel out. There and there. So we get limit as x approaches infinity, 1/4 in front of cosine 1 over 4x squared. Much better. Okay. Cosine as x approaches infinity in the denominator is going to go to 1, isn't it? Right? Because as we get insanely bigger in the denominator, that goes insanely smaller. So cosine as we approach insanely small, as x goes to infinity, will give us just 1. So we have a lovely 1/4 to go with that. So directly, we can't really do indeterminants of 1 times infinity or infinity minus infinity, but we can simplify by dividing by the reciprocal and finagling it algebraically so that we can, in fact, apply L'Hopital, derivative of the top and the bottom, and then apply the limit.